It's time to prove our first results concerning open sets. First, we'll prove that if we have an arbitrary collection of open sets, their union is also an open set. Then we will prove a similar result for intersections. We'll prove that if we have a finite collection of open sets, their intersection is also an open set. Recall the definition of an open set, which I have put here, and I'll leave a link in the description to my lesson introducing them if you need a more thorough recap. We say that a subset of the reals U is open if for every element x of U there exists a positive number delta, so that every number that's less than delta away from x forms a subset of that set U. Or stated another way, we say U is open if for all elements x of U, there exists some delta neighborhood around x that is still a subset of U. That's what an open set is. With that said, let's get into the proof of the first result, that an arbitrary collection of open sets is an open set. So this collection of open sets could be finite or infinite, countable or uncountable. To begin the proof, we need to take an arbitrary element from the union of this collection of open sets. If it doesn't have any elements, then it's the empty set, which we've already discussed is an open set. So if we take this element x from the union of the collection of open sets, remember the goal to show that this union is open will require us to prove that there is some delta neighborhood around this element x, which is entirely contained in the union of open sets. Alright, so if we've got x that's in this union, what we know for sure is that x must belong to one of the open sets in the union. Right? X can't be in the union unless it belongs to at least one of the open sets that's in the union. Now, since X is an element of this open set UK, by definition, there must exist some neighborhood, say V delta K, of X, which is a subset of UK. That must be true since UK is open, so any element from it must have a neighborhood that's contained in the set. However, we know that UK is also a subset of our union of the open sets, because the union just contains everything that's being unioned, so UK is certainly a subset of the union of open sets. But that means that this neighborhood around our element X is a subset of the union. Since we took an arbitrary element from the union and showed that it must have some neighborhood which is a subset of the union, we can say, therefore, we've proven that this union of open sets, the union of every open set U alpha over all values of alpha, is an open set. I'll just write that it is open. Now we want to prove that if we have a finite collection of open sets, U1 through UN, then the intersection of all these open sets is also an open set. Similar to the previous proof, we have to begin by taking an arbitrary element from this intersection. So let's take X from the intersection of all the open sets UK. So that's from K equals 1 all the way up to N. Now, we know that since X is in the intersection of all these open sets, X must be an element of every single open set in the intersection, by definition of intersection. X can't be in this intersection unless it belongs to every single one of those sets. So X is an element of each one of these open sets UK. Then, since each of these is open, by definition, for each UK, there must exist a positive number delta K, so that the delta K neighborhood of X is contained in UK. Some of these deltas might be quite large. Perhaps delta 3 is really big. If that were the case, then it's probable that the delta 3 neighborhood of X probably wouldn't be a subset of some of the other open sets in the intersection. Maybe it's not a subset of U2, although it is a subset of U3 by definition. However, if we take the smallest of all of these deltas, that for sure is going to have to be contained in all of the other open sets. we need a delta neighborhood of X that's contained in all of these open sets. That way it's also contained in the intersection. So what we'll do is let our delta be the minimum of all the deltas for the individual open sets. So it's the minimum of delta 1, delta 2, and so on, all the way up to delta n. Again, we know that every one of these open sets has some delta neighborhood around X that's contained in the set. We want to pick the smallest one to make sure that our delta neighborhood is not too big to be contained in all of the sets. So if we let delta be the minimum of all of the deltas for the individual open sets, then our delta neighborhood around X will surely just be a subset of each delta k neighborhood of X. And each delta k neighborhood of X is a subset of the corresponding open set UK. In a picture, what we're doing might look something like this. Here's our number X. Some neighborhoods around X might look like this. Perhaps that's the neighborhood of X that we've got in the set U1. Maybe the neighborhood we've got in the set U2 is a little bigger. Maybe it looks like that. So we wouldn't want to pick the delta 2 value from that open set U2 because this bigger neighborhood would go outside of this smaller one. And again, we want to make sure that our delta neighborhood is contained in every single open set. So we're going to choose the minimum. Now, in doing that, like we said, that means our delta neighborhood of X is going to be a subset of every one of our open sets UK, and by definition of set intersection, that means that our delta neighborhood of X is going to be a subset of the intersection of all of our open sets. By definition, then, this means that our intersection is open. So I'll write those 3 dots. That means, therefore, our intersection of this finite collection of open sets is also open. We took an arbitrary element from the intersection and showed that there exists some neighborhood around that element, which is a subset of the intersection. So the intersection is open. That's how you prove these 2 basic results concerning open sets. Let me know in the comments if you've got any questions about the proofs or if you've got any video requests.
Head in the clouds like a little balloon, scaling the stratosphere.